Now let's look at the next example, minimum following path sum 2. So there is another question called the minimum following path sum, which is easier than this one. So I encourage you to do that yourself. So in this problem, we are given a grid of integers, and a following path is one where we go from the top row to the bottom row, and we pick one element from each row. And here, the requirement for the path, it has a non-zero shift. So that means no two elements chosen in adjacent row are the same. So for example, if we just want a minimum following path in this array, then certainly we will pick the leftmost one. We'll pick 1, 4, 7. However, because we require this has a non-zero shift, so if we pick 1, the next one cannot be 4. It can be any of the other 5 and 6. So in order to get to this minimum path, so then the best way is to pick 1 and 7. And then we will not pick the minimum element on the second one, so we can pick the second minimum, which is 5. So then we have the path 1, 5, 7. So that gives us an output of 13. So that's the problem. I encourage you to pause and think about how to solve it. And in fact, I encourage you to try to solve it on LeetCode first. Okay, so let's apply the same method that we used in the previous problem, where we define something that gives the solution to partial problem, and then see how we can gradually construct the final solution. So suppose we have the answer for ending at the ith row, because to me that seems a very natural way of defining partial solution. We are following one row at a time. So if I want to compute the best answer for following until that current row, then hopefully I can use that information to build the solution for the next row. So suppose we already have the information for a solution ending at the ith row. Can we use that to obtain a solution for ending at the i+1th row? If I already know what is the minimum following path satisfy the condition for ending at the second row, does that help me compute the answer for the final one? So of course, the minimum path ending at the second row is we'll have a sum of 5. So 1 plus 4, that is 5. However, I cannot use that. That's not enough information for me to figure out the answer for the third row, because I need to know where does that path end in order to determine whether I can use that. So in fact, in this case, the path ends at 4. So I don't really, that's not enough information for me to figure out whether what is the minimum sum for following path ending in the third row, because I would want to use 7 from the third row, but if but I cannot use the path ending at 4 if I want to use 7. So if I want to use 7, then I need to find another path ending at somewhere else on the second row. So there's not enough information when we just define the thing we are maintaining as a solution for ending at the ith row. So we need we need to maintain actual information, or we can define we can define the relation to be a little bit more fine-grained, so that actual information is already there. So here I'm taking the approach of defining the information more fine-grained, defining dpij to be the minimum sum ending at row I and column j. Now, how do we compute this dpij? So encourage you to pause the video and try to write the mathematical definition of dpij. And then our program, of course, will just be turning that math formula into code. So, of course, dpij will have a part which is aij, which is the last cell that I'm ending at. So along the previous row, then I want to pick the one that has the smallest value. However, that has to be one that's not ending at the same column, because I have to shift for going from every row. So then this is my mass definition. So it's a minimum value of dp I minus 1k, where k is all possible value except j. So that's the that's my dp definition. And then I think my first version of the code I'm showing, which is essentially just turn this into Java code. So this is Java code. So yeah, there's a special case when n is 1. We don't need to do anything. I'm initializing the first row as just the first the data in the given first array, and then for every ij, I want to compute dpij, but dpij need this mean value. So these two lines in purple are computing the minimum value ending at I minus 1k, and when k is not equal j. So that's computing that, and then dpij equals this. And another thing that's interesting about this the problem is, given we define dpij this way, finding out the final answer, actually we cannot just look at one cell to find out the final answer. The final answer will be the minimum value among the last row. So among all the dp n minus 1j's, I want to find the minimum value. So that's this two, whatever this color is, these two lines does. So when I was doing applying dp in the early phases, sometimes I find that I got stuck in that I want to define a dp relation where the final answer is just a simple lookup, but it doesn't have to be. So I can define the relation in a way that's easy to compute, and the final answer may require sort of going through all the value I've computed, or at least some part of the value I've computed, and computing the final answer. So a question is, what is a computational complexity, time complexity of this code? Encourage you to pause to come up with your answer. So the complexity is n cubed, because we have a loop from n at here, loop n here, and then another loop here from 0 to n minus 1. So it's an n cube. Can we speed it up? Of course, the answer is yes. I noticed that whenever I ask a question, can we speed up? The answer is always yes. Maybe I should sometime ask question, can we speed it up, where the answer is no. But that's a little bit dangerous, because you never know whether it's not you never know. It's very hard to say this is the best you can do for this problem. So this is proving a lower bound on the problem. This is very hard to do. So how do we speed it up? And generally, when you try to speed up things, you try to find out, are you doing the same computation again and again, and they are kind of wasted. So the answer is yes, because we keep trying to find the minimum among this row. It's just that every time we want to find something that's not the current j, but this kind of comparison we're doing a lot. So one thing to notice is that suppose we have the minimum without consider this constraint, then that actually can be used for all the cells. Suppose the minimum is achieved at the column, say k, column k. Then that can be used for any j value dpij here where j is not equal k. But for dpik, then I need a second minimum, because I cannot use the smallest. Then I have to use the second smallest. So this is what I did in version 2, where the code in purple now compute both the minimum and the second minimum. And here I'm just keeping track of the indices, the indices into the dp array for this minimum and second minimum. So start by assuming 0 is the minimum, 1 is the second minimum, and then If the first one turns out to be bigger than the second one, I'm going to swap them. And then I will scan through the rest, and anything that's less than the minimum, then that becomes the minimum, and the current minimum becomes the second minimum. And otherwise, if it's less than the second, so that becomes the second minimum. So then here, the next loop just use the minimum. K0 is the minimum. And then for K0, we're going to use the second minimum. So constructing the answer is the same as version 1.